Welcome to G Fun Facts Online. What if I told you that we can listen to glaciers? Not just watch them from satellites, but actually hear them groan, crack, and collapse in real time. This isn't science fiction. It's the incredible field of cryoseismology, the science of listening to the symphony of the Earth's frozen regions. We used to think of glaciers as silent, slow-moving giants. But by planting sensitive microphones, called seismometers, on and near them, we've discovered that they are incredibly noisy. They generate a constant stream of vibrations, from tiny crackles to planet-shaking booms, that tell us a story we could never see with our eyes alone. Today, we're going to tune into the secret sounds of the ice and explore the futuristic technologies that are turning our entire planet, and even other worlds, into a listening station. When a building-sized chunk of ice breaks off a glacier, a process called calving, it obviously makes a huge splash. It also sends powerful seismic waves vibrating through the Earth. For a long time, scientists thought this was a straightforward relationship. Bigger iceberg, bigger earthquake. It seemed like a perfect way to create a remote ice loss meter. We could just listen from thousands of miles away and calculate how much ice was falling into the ocean. But the reality, as scientists discovered at places like the Jakobshavn Glacier in Greenland, is far more complex. It turns out that the magnitude of a calving-generated earthquake isn't always directly proportional to the size of the iceberg. The style of the calving event plays a massive role. Did the iceberg simply tip over? Did it slide off gracefully? Or did it shatter into a million pieces? Each of these styles creates a completely different seismic signature, even for icebergs of the same volume. Furthermore, the shape of the fjord, the narrow, steep-sided inlet of the sea where the glacier meets the ocean, also changes how those seismic waves travel. It's like trying to figure out how big a rock someone threw into a pool just by listening to the splash from another room. The sound is muffled, it echoes, and the shape of the room changes everything. This complexity means we can't just use a simple formula to measure ice loss. To truly understand what the glaciers are telling us, we need to listen more closely, with more advanced tools. And that's exactly what's happening. The future of glacial seismology is being driven by mind-bending new technologies. Perhaps the most exciting is a technique called Distributed Acoustic Sensing, or DAS. This technology is a complete game-changer. It transforms standard fiber optic cables, the same kind that deliver high-speed internet to your home, into a dense array of thousands of individual seismic sensors. Imagine a single cable, kilometers long, acting as a line of thousands of microphones, each just a few meters apart. Here's how it works. A special instrument called an interrogator unit sends a pulse of laser light down the fiber optic cable. The glass fiber isn't perfectly pure. It has tiny, microscopic imperfections all along its length. These imperfections reflect a minuscule amount of that laser light back to the interrogator. This creates a constant, stable baseline of backscattered light. Now, when a seismic wave from a tiny icequake or a massive calving event passes through the ground, it ever so slightly stretches or compresses a section of that fiber optic cable. This tiny deformation changes the travel time or phase of the light being reflected from that specific point. By analyzing these phase shifts along the entire length of the cable, scientists can measure the strain with incredible precision and pinpoint exactly where the vibration occurred. The level of detail is staggering. Instead of placing one expensive seismometer every few kilometers, DAS provides a continuous measurement. Scientists have already begun deploying these cables by drilling them deep into the Greenland ice sheet and stretching them across glacier surfaces. They've even used DAS to discover previously unknown types of icequakes happening deep within the ice, events that were completely invisible to older methods. The technology is providing ultra-high-resolution data on how seismic waves travel through the upper layers of snow and compacted fern, giving us a clearer picture of the glacier's internal structure. And the potential doesn't stop at the ice edge. By tapping into the vast network of existing telecommunication cables that already crisscross the ocean floor, DAS holds the promise of monitoring offshore seismic activity and calving events at a scale we've never dreamed of before. We could listen to the entire coastline of Greenland at once. But having revolutionary new ears is only half the battle. The sheer volume of data coming from technologies like DAS is a tsunami of information. Far too much for any human team to analyze manually. This is where artificial intelligence and machine learning come in. For years, scientists have used simple algorithms to help classify different types of icequakes. Was that vibration a calving event, a crack forming, or just the rumble of water flowing beneath the ice? But the next generation of AI will do something far more profound. It will learn to predict these events before they happen. By training machine learning models on vast catalogs of seismic data, combined with other environmental information like temperature, melt rates, and ocean tides, scientists hope to identify the subtle, almost invisible seismic precursors that might signal an impending disaster. Imagine an early warning system that could tell us a catastrophic calving event is imminent, or that a glacier is about to enter a dangerous high-speed surge. This could be critical for protecting shipping lanes, infrastructure, and communities living in the shadow of these frozen giants. This brings us to another key part of the future: collaboration. Seismology can't tell the whole story on its own. The real breakthroughs are happening where different fields of science merge. Seismic data is being combined with hyper-detailed satellite imagery, pinpoint GPS measurements tracking the ice's movement, and oceanographic data on water temperature and currents. All of this information is then fed into sophisticated computer models of ice flow. Think of the seismic data as providing the crucial ground truth. The biggest uncertainty in our models that predict future sea level rise is often a poor understanding of what's happening at the base of the ice sheet, miles below the surface. We can't see it, but we can hear it. Seismic observations are uniquely positioned to fill this gap, telling the models what the physics at the ice bed interface really look like, making their predictions far more accurate. And the knowledge we're gaining isn't just for understanding our own planet. The field of cryoseismology is looking outward, to the stars. The icy moons of our outer solar system, like Jupiter's Europa and Saturn's Enceladus, are some of the most fascinating destinations in our search for extraterrestrial life. Scientists believe these worlds hide vast liquid water oceans beneath their frozen shells. Future space missions like NASA's Europa Clipper may carry seismometers to listen for icequakes on these alien worlds. Any signal they detect, a crack, a tremor, a plume eruption, would be invaluable. The science of cryoseismology, developed here on Earth's glaciers, is providing the essential knowledge base, the dictionary we will need to interpret what those first faint signals from another world might mean. So what have we learned from listening to the ice? We've learned that glaciers are not the silent, static monuments we once thought. They are dynamic, noisy systems that communicate their every move through the language of seismic waves. We've gone from simply observing their surface to listening to their internal mechanics. We can now hear the deep, resonant booms of glacial earthquakes, giving us a real-time measure of the colossal icebergs being shed from Greenland and Antarctica. We've detected the rhythmic, twice-daily seismic pulse of Antarctic ice streams, revealing their surprising stick-slip dance as they're pulled and pushed by the ocean tides. We've used the constant chatter of tiny icequakes to illuminate the fractured, crevassed landscapes of alpine glaciers, and to pinpoint the sticky spots on the bedrock that resist the flow of colossal ice sheets. We've even learned to interpret the continuous, ambient hum of the ice, turning what was once considered background noise into a tool for monitoring the subtle seasonal shifts in a glacier's health. This newfound ability to listen is more critical now than ever before, because the stories these glaciers are telling are tales of rapid, profound, and alarming change. The rising tempo of glacial earthquakes, the shifts in seismic tremor tied to increased meltwater, the very groans of the ice as it thins and accelerates. This is the planet's own seismic data stream, recording the impacts of a warming climate. By continuing to refine our instruments, hone our analytical techniques, and most importantly, by listening closely, we can better understand the forces that are reshaping the frozen regions of our world. we can better prepare for the future that their resonant voices foretell.